today we're going to take a look at what are you going to do if you have to graph something that has a phase shift. We've pretty much done everything but that up to this point. And so let's just go ahead and take a second here and let's determine for this graph right here, amplitude, period, and phase shift. Let's see if we can figure that out. So amplitude for this graph would be what? Nope. Yeah, 1, right? Is that understood, right? Amplitude's 1. So period. Again, the period really means how long is it going to take before it starts repeating what it started with. Or we kind of talked about it as how long until you hear the whole song, right? And what's sine's normal period? 360, but now I'm going to hear the song twice, right? So it's only going to be 180 degrees to hear it once. And does this have a phase shift? Yep, it has a phase shift of how much? Positive 45. Now, what I like to do is if I was given this problem, I would say to myself, all right, let's see if I can figure out what it looks like before the phase shift, like in a little sketch, and then just shift it over, is what I would do. And so how would I, looking at this equation right here, what would I have to do to that equation to get rid of phase shift? What would I do to make the phase shift go away? Not even like legitimate algebra. Just flat out, how would I make it go away? Scribble it out, right? Okay. Or make it a 0, right? So in other words, it would be y equals sine of 2 theta would have the same amplitude as what I have, right? Would it have the same period as the one I have? But it would have a different phase shift. There wouldn't be any, correct? So what I'm showing you right now is not like a legitimate algebraic way of solving this problem. This is a strategy of getting the graph. Okay, is everybody clear on that? So really, in this problem, we are eventually going to come back and do that problem. But first, we're going to go and do a different problem. And that problem we're going to go do is y equals sine of 2 theta, because that would be no phase shift, correct? And just take a look at what graph you happen to have on the bottom. Y equals sine of 2 theta. There it is. So we're going to do this one first, and we're going to then take this answer and just shift it however much we're supposed to. Okay, yes, question?
So it would be like, would you be able to push the 45 over, like almost add 45 to the right side,
okay,
and to the left side, so it would be like 5 plus 45 degrees equals sine 2 theta? Is that kind of the...
Very good question that came up is, can we add that 45 degrees? We're back on this one now. Can we add that 45 degrees to the other side? And unfortunately, no. Because that trigonometry, that sine, has that kind of captured at this moment. It has all of that stuff captured, and so I'd have to undo all of that. So then we start talking about arc sine and all of that stuff, and that's not what we want to do right at this moment. Okay, yep, good question.
Minus 45, would that pretty much become your new 0?
What do you mean the minus 45 becoming your new 0?
Like,
Positive 45 gets you back to 0, if that's what you're thinking.
because it says theta minus 45 degrees.
Mm-hmm.
So if you just subtract 45 degrees from the 0, from where your x and y axis cross,
Mm-hmm.
wouldn't that pretty much become your new...
Okay. What some people do like to do, and I think this is what you're trying to say, the question is, once we put stuff in, wouldn't it kind of become our new starting point? What a lot of people, and some people do, is they do just make a theta y table and they go and they do the graph. And if you're comfortable with that, you can do that. That's fine. Make your own here. But my idea of doing it this way is so that you can actually see the phase shift instead of it just being words that you use. Okay? Good questions. And I'm actually going to do it a couple different ways. So let's go graph this one first. Y equals sine of 2 theta. Well, we know the amplitude already is 1. And the period we already know is 180, right? So over here is 180. And again, I'm going to show this to you a couple ways, and then you figure out which way works for you. Well, unless this way works for everybody, maybe we'll just stop with this one. And this is sine's graph, correct? And we know that it would be 1 up here and negative 1 down there. And where does sine normally start? Does that start at the origin, or does that start off the origin? Which one is that? Yeah, at the origin, right? It kind of starts right here. Now, what if you forgot? What would you do? Well, you put in some points and find out what happens, right? And then what does sine normally do? Once you go to that first tick mark, where does it go? It goes up. Yeah, it goes up to whatever your amplitude is, right? Then what does it do? Yeah, it comes back down, and then it goes over to here, then it goes over there. So you see why I like to come to these, because as I can tell just by talking to you right now, you're actually pretty good at understanding how to do these, right? You got a pretty good grasp of what this is going to look like. So there it is, correct? Yeah, that's actually not too bad. I didn't get too much different size on either side that time. So are you with me that that's this one, correct? So now what I have to do is basically, you see all that red that I have, at least the graph? I basically have to pick up that red, leave the axis there, pick up that red stuff and move it 45 degrees to the right, and then put it back down. Is really what I have to do. So let's see if this works. Hopefully the technology works for me here. Ooh. Well, that wasn't what I was looking for. Nope, that's not what I was looking for either. I just have to get out. There it is. Yeah, this is probably not going to go well, but we're going to try it anyways. Do you agree that's my little sketch of what y equals sine of 2 theta looks like, right? Okay. Because obviously you have it right below there. You can see it, and I couldn't. I'd be flipping back and forth. That's why I did that. Okay. So now what I basically have to do is if I ever move it to the right, what I do is I start on the left. Does that make sense? Because then I can move everything to the right. So you see how at negative 180 down here, it was at 0, correct? What I have to do is I have to move that point. How far? I have to move it 45 degrees to the right. So where would that end up? This 0 doesn't stay here. It ends up, it just happens to be one tick mark, right? Just coincidentally. It actually ends up right there, agreed? So that's what we should do. Let's go here, and this is negative 180, right? Negative 90. Do you read that point right there is here? You with me on that? How it just basically, I moved it to the right 45 degrees, right? So let's just take the easy points. What's another pretty easy point to move? This negative 90 is a pretty easy point to move, don't you think? Where am I going to move it to? It's not going to be at negative 90 anymore. I have to move it to the right 45, so it's going to be at negative 45, right? If I just move it that way. Now, don't think it's always going to be just, oh, just move it one tick mark. Okay, that's not always how it's going to work. Now, what's it supposed to do? I just graphed these 2 points. Agreed? Basically, these two, well, those 2 points, right? It should go up between them. You agree with that? That's what it's supposed to do? Or in other words, I have to move this point over 45 degrees, right? Are you with me on this? Or is, okay, well, nobody's saying a whole lot. So either you're really getting it or you're really not. It's one of the two, right? So this would go there. Agreed? Well, at this point, just our knowledge of sine pretty much has us being able to finish, right? So how about this one? Where does this one end up? Move it 45 degrees that way. And you're right here. Well, now what's going to happen at this next tick mark? Where's it going to go at this, what is this, 20, nope, 45 degrees right here? Well, where's it going to go? Yeah, right here, and then it's going to go up, then back to here, then back to there. I think somebody said it looks like an M. Isn't that what somebody said when they got done, right? What? What? Oh, yeah, that's a little low. Sorry about that. A little higher. There we go. Was that what was bad, or was it something? Oh, well, I think you can handle it being bad. Well, and then I don't even hit the point, so what was the point of you making it over there? There it is. There's the graph with a phase shift. The reason I want to show you both of them is you see basically down here, that's what phase shift does. Oh, I didn't think it was going to do that. It just moves it up and slides it over, one way or the other. Yes?
Say you had a phase shift of the original, like, okay, we had the y equals sine of 2 theta.
Yep, okay.
So you phase shift, like, 90.
Okay.
And split, or, what, it would like start down, so that's what should cosine or no?
Oh, good question. Sine and cosine are very, I do exactly know what you mean. Sine and cosine are very, very closely related. And I can maneuver a sine graph to make it turn into a cosine graph. Most definitely. So you're saying move it 90 degrees. Is that what you're saying? To which way?
It would be 45 back, so it would be sine
Because here's something I can do up here that you can't do on your paper. I can just move the axes in the background and have it do what you want it to do.
Yeah.
Okay. So you're saying, what if I just move it like that?
Yeah.
Yeah. Yeah. Sine and cosine are just 90-degree shifts or 45-degree shifts of each other, depending on. We have a 2 theta there, so it would only be a 45-degree shift. Normally, it'd be a 90-degree shift. Exactly. There's cosine. Right? Perfect. That's cosine of 2 theta right there. Exactly.
It's not a good matter right now.
Not really. You can challenge yourself by writing it either way. Okay, that's completely up to you. But normally sticking with whatever you've been told is a lot easier. But yeah, you can write it many different ways, definitely. You can do the same thing with secant and cosecant, just shift things over and it turns into the same thing. Okay, very good question. Does everybody see what she's talking about? Look at that, it's cosine right there. And all I did is I moved the sine graph a little bit, right? Very good, excellent. Now, what some people do though, and this is okay, some people like to do the little sketch and then come over. Did that work for you? Do a little sketch off to the side and move over? Some people do that. But here's what other people do. Some people like to do this. They actually put the other one in here and they just make it dashed like this. But I didn't know if that was going to be too much for you to see both graphs on the same axes. This green one is right here. It's that one. But I didn't, well, I really messed that up. I didn't know if that would be too much seeing both graphs on the same axes. Because it gets really confusing once you start putting asymptotes in. When you have two graphs, then you got asymptotes and you got stuff everywhere, right? But can you see the shift now? Go from the green to the blue. You see how that's a 45 shift to the right. Right? Okay. So did you find one way that's going to work for you? All right. Well, let's try another one, and then I'll let you loose. Okay. So if I was going to do this one, let's just do our amplitude, period, and phase shift again, and then we'll see maybe what our strategy would be. Amplitude.
No, it doesn't have one.
Ah, very good. Almost got you. It's tangent. Yep, not applicable. Well, it's because it's not measurable, right? Does the 4 that's out front still play a role? Yes, it does. Okay, it still multiplies things by 4, but it's just not measurable. All right, so how about period? Very good. I wanted to see if somebody was going to say 180 on this one. But tangent's normally 180, correct? So divide it by 2, because I'm going to hear it twice, so it'll only be 90 degrees. Okay, and we do have a phase shift, I see. Yeah, negative 45 degrees is how I think a lot of us like to think of it, right? Or you could say negative pi over 4, right? It's the same thing. Okay? But then if you're going to say negative pi over 4 for your phase shift, you're probably going to say pi over 2 for your period. Right? You're going to say it one way or the other. Okay? And so we know that we got 90 out here and negative 90 here. Now, if you're one of them that's going to go ahead and substitute values in, and I don't really have a problem with that. If that works for you, that's fine. And what I mean by that is make your theta y table and do it. That's fine if it works for you. But based on my strategy, what we would do is graph everything but the phase shift and then just shift it over. Right? And again, the phase shift is that pi over 4. Okay? So why don't we go ahead and graph this next one, which is why I also have it on there. You see, it has the same amplitude. It has the same period, right? It's still not applicable there, but it's basically the same graph otherwise, right? So here we go, 90, 45, negative 45, negative 90. Now, I know that you haven't dealt with tangent as much as I have, okay? Sine and cosine, it seems as though you're getting very good at them now. You're starting to know what they look like and know what to expect. Tangent's still kind of that strange one, right? So maybe we should take a second here and just get an idea of where things are going. Kind of more old school here. And there we go. So let's just start with 0, right? So 0 degrees. So you put 0 right there. You take it times 2. Well, that's still 0. What's tangent at 0? Well, I went to the unit circle over here. How does the unit circle, again, help us find tangent? How do you do that off of the unit circle? Yes? Yep, sine of theta over cosine theta, or sine of whatever angle you're looking at, right, over whatever cosine of that angle. And so sine over cosine would be 0 over 1, correct? Sine over cosine. So 0 over 1 is 0, and then I take it times 4. Well, it's 0, isn't it? Well, there we go. Right there. Now remember, it was a little scary the other day with tangent when we had to go to the tick mark, so it really wasn't that bad, right? Because this tick mark right here is not the best value in the world, right? It's unfortunately 22.5. But am I going to take tangent of 22.5? No, right? I get to multiply first, right? So you put 22.5 again in there for theta. times 2 is 45. So I got to take tangent at 45 instead. And that one, wow, I didn't leave myself a whole lot of room. Well, that one's square root of 2 over 2 and square root of 2 over 2, correct? So if I do sine over cosine there, what do we got? We got 1, right? But then I still have to take 1 times 4. So 4. So this is here, and so we'll put 4 up there. So you see how the 4 is still important, though, right? It makes it go up 4 times faster than it did before. But it's still really not measurable because it just keeps going on forever and ever. Anybody want to take a wild guess what's going to happen at 45 degrees? Yes? A no solution, exactly, which turns into asymptote, right? Because no solution means you better not put a point there, is what it's saying, right? You're not supposed to get something. Well, let's just make sure. 45 degrees, we put it in there, times 2 is 90. Up there, that's what, 0, 1, right? Well, 1 divided by 0, that's undefined. So that's no good. So in other words, do not put a point here. And remember, if you graph this on some software or something, is it necessarily going to put that asymptote there? No, it's just a boundary line. It's not actually part of the graph. It's saying don't graph here. Well, I don't know about you, but my knowledge of tangent has me feeling pretty confident in this graph already. Because what did tangent look like again? It looked like the cubic, right? So what do you think is going to happen over here at negative 22.5? Where's it going to go? Yeah, it's going to be down here, probably at negative 4, right? And so there's that cubic that somebody kind of drew in the air, right, when I asked the question. How about negative 45? What do you think is going to happen there? Asymptotes. Okay, so you see how knowing what these graphs look like saves you so much time. Okay, now we get some tricky ones, though. How about over here at, what is that, 67.5 over there? Where's that one going to go? If it follows this pattern, it's going to be at negative 4, right, down here. And if it follows the pattern 90, it's going to be back up at 0, right? A lot of people get this one wrong over here, though. So once you get that drawn, if I could have you draw your attention over to this one. That's these two over here, this negative 90 and the negative 67.5. Yeah, more up, right? A lot of people want to put it down for some reason because the other one over here is down on the right side. But yeah, this one is kind of that other part of that one, right? Well, there it is. Okay. Any questions on any of that we graphed there? So now you can see why I've kind of formulated and set this up the way I have. It's all really leading towards this, doing the phase shift. Because if you can do this, and again, I'm going to try and copy this thing over, although I struggled last time. Uh-oh. Right, that's like this is almost like picture in picture, right? For your television. Whenever I have something with asymptotes in it, that's normally what I move first. Okay, so what am I supposed to do with my asymptotes according to this phase shift? Move them, yeah. 45 degrees to the left. Okay, so it was at 45 down here, right? So if I move it 45 left, well, that actually works out pretty nice, right? I mean, that's a 0, right? That's right here. I don't know why I went to blue when all the rest was green, but so now here's the other one, right? At negative 45. So if I move that 45 to the left, I'm at, where's that end up? Negative 90, right? So I think there's probably one more asymptote that fits on the graph now because it kind of slid in from stuff that we didn't see before, right? Yeah, at 90, right? Boy, we better have a pretty good knowledge of tangent by this point, right? That is what's going to happen. What's going to happen at these negative 45 and positive 45? Those are going to be at the zeros, right? And then it's just going to pretty much make your... Yep, cotangent is the one that kind of snakes the other way, exactly. And once I know everybody's done with this one, I'll throw a cotangent in there quick so that you can see it. And just like that comment that was made before, we can kind of make cotangent out of tangent and back and forth with, you know, very cleverly positioned negatives. Because that one we do have to flip. Okay? Is everybody clear that this is the answer to this question? So that when I erase it and put cotangent in, you're not confused? That'd be good? Okay. Again, yeah, cotangent is the one that would snake through the other way like that. Yep. And your cosecant and your secant are the ones that have the asymptotes, but then parabolas in there, right? Okay. So any questions on that? Now what's going to happen on your worksheet is I'm not going to give you like I did here. I'm like, oh, we're going to do this one, so let's go do this one first. Okay, so you don't have to do it that way if you don't want to, or you can just do these little sketches off to the side. That's up to you. Or some people actually like to put them both in there, but as you can see, if you had two graphs here with asymptotes all over the place, it would be very confusing, right? If I tried to put this one down here on top of that one there, it would just get to be a lot, I think. So you need to choose what's going to work for you. Any questions?